Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of river sizes. This is, by all accounts and measures, one of my favorite questions. It's a classic graph traversal question. Basically, you're given a matrix, in other words, a two-dimensional array, that doesn't necessarily have an equal width and height. And the matrix contains only zeros and ones. Every zero represents a part of land, and every one represents a part of a river. And a river basically consists of a bunch of ones that are adjacent, right next to each other, either horizontally or vertically. And you have to write a function or an algorithm that is going to return an array of all of the sizes of the rivers contained in the matrix. So in the example matrix that I've got in front of me here, we can see that there are about 5 rivers, or not about, there are exactly 5 rivers. And they're of sizes 1, 2, 2, 2, and 5. So here in the top left corner, we can see a river of size 2, because there are 2 ones next to each other vertically. In the bottom left corner, there's another one. Here on the far right, there's another one of size 2. Then we've got this one of size 5 here that kind of extends horizontally and then vertically. And finally, we've got the one here that's a river of size 1. And you'll notice that even though it's adjacent diagonally to another one, that doesn't mean that it's part of a greater river, because the prompt specifies that they can only be adjacent horizontally and vertically. So how do we solve this question? Well, the naive approach would be to just traverse the matrix row by row, right? And entry by entry. So we'd start at this one, then at this other, then at this 0, then here, here, here. Then we go to the second row, third row, etc. And to just keep track of all of the ones somehow. Now, that sort of maybe works, but it starts to fall apart when you realize that you need to keep track of all of the ones that you've seen, and you need to keep track of which rivers they're a part of. Because these ones here that form a river of size 2 have nothing to do with, let's say, these ones here, or the ones in the middle here, right? So you need to somehow keep track of that. And that's where treating this matrix and this problem as a graph traversal problem really shines. So if you treat this matrix as a graph, you can treat every element in this matrix as a node in the graph, where each node has a value, either 0 or 1, and each node has neighboring nodes, right? The node right above it, right below it, to the right of it, and to the left of it. So if you look at, let's say, this node here that has a value of 0, it has 4 neighboring nodes. 1 immediately above it, 1 to the right of it, 1 below it, and 1 to the left of it. And so what you can do is you can traverse this matrix or this graph, and at every node, you check its value. If the node has the value 1, then you know that it must be part of a river. And at that point, you can apply the graph traversal algorithm of your choice. So either breadth first search or depth first search. And here I'll make a little pause and say that if you're not familiar with breadth first search or depth first search, I highly encourage you to go check those 2 questions out right here on algoexpert.io, because they're essentially prerequisites to this algorithm. But so whenever you encounter a node that has a value 1 and that is therefore part of a river, you can start applying breadth first search or depth first search and exploring that particular node's neighboring nodes. And if any of its neighboring nodes are also nodes of value 1, then you're going to apply breadth first search or depth first search to all of that node's neighboring nodes. Okay? But you're only going to do so every time you encounter a node of value 1. Because that means that it's part of a river. And so what that means is that as you explore the matrix, right, whenever you encounter a 1, you will inevitably traverse, either using breadth first search or depth first search, all of the ones that are part of its river, right? And then whenever you encounter zeros, you just stop. You don't go further than that. So let's just look at what it would look like in practice, right? Imagine you were at this node here, this one here in the middle, right? So you're traversing the matrix, you get to this one, okay? So you know that you're part of a river now, and you look at all of this one's neighbors. You look at the one above it, it's a 0. You look to the left, it's a 0. To the right, it's a 0. So far, we haven't found any neighboring ones to this one. But then you look below it, and you've got a 1. Okay? So now you start traversing this one, and you'll continue to apply your breadth first search or depth first search algorithm on this one. Okay? So now you look at all of the neighbors that we haven't looked at of this one, and so to the left of it, you've got a 0. To the right of it, you've got a 0. Above it, you've got the one that we just came from, so you kind of ignore it. And I'll dive into how you do that in a second, right? Algorithmically, how do you know that you've kind of already taken into account this one here? And so then you go below it. Now you've got another 1, right? And you do the same thing. You look to the left, it's a 0. To the right, it's a 0. Above it is the one that you just came from, so you ignore it. And then below it, you've got another 1. So we can just underline it. And now we apply the same algorithm once again. Look to the left, it's a 0. Above it, we just came from here. Below it, there's nothing. We're outside of the matrix. And finally, to the right of it, we've got another 1. And then you can kind of finish here because all of the other neighboring nodes are 0s. And so now you've encountered 5 1s, and you've kind of kept track of them by incrementing some kind of variable. We'll dive into that when we're doing the code walkthrough. But so now you've found that you've got a river of length 5, or of size 5. And that's how you can basically find all the river sizes. But now the second tough part of this algorithm comes where you realize that you're going to explore a bunch of nodes multiple times if you're not careful, right? Because as we just saw, when we were at that second node, so let me erase all of these. When we were at the first one here, we explored above, to the right, to the left, and then below. And then we got here. And when we were at this one, we explored the left, the right, and below. But then I told you guys, forget about the top. Forget about the one above because we just explored it. But how do you know that you just explored it, right? How do you keep track of that? Similarly, imagine that weren't an issue for a second, and imagine that we had explored the entire river here, and we had gotten a river of length 5. And then we continue to traverse the rest of our matrix. So I'm erasing all of these, and we continue to traverse the rest of our matrix, probably row by row. So we go here, 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 there's nothing. And then we get to this one. Okay? We've already explored this one, right? We've explored it as part of this river of size 5. So how do we know not to explore it again? Well, that's where we're going to employ a very common and extremely practical technique that's very commonly used in graph traversal problems, which is we're just going to keep track of all of the nodes that we visited. And if we ever encounter a node that we've already visited, we just skip it. We don't perform any sort of computational, any sort of hard computations on that node. Okay, so let's see what that looks like. We're going to start at the top of the matrix, and I'm going to traverse it and apply some kind of variation of breadth first search or depth first search for the sake of the video. I won't necessarily respect the exact order in which I traverse nodes, just for the sake of the video. But overall, I'm applying, some variation of depth first search or breadth first search. And I'm also going to keep track of the nodes that I visited by underlining them in purple. So we'll start at the top node, the node in the top left corner. And we'll underline it immediately in purple. This means that we've visited this node. And we notice that its value is 1. Okay? So now we are going to visit its neighboring nodes. Okay? So it has 2 neighboring nodes, because above it, we're out of the matrix, and to the left of it, we're out of the matrix. So if we're applying some kind of depth first search or breadth first search algorithm, we're either going to recursively traverse the neighboring nodes, this 0 and this 1, or if we do it iteratively, we're probably going to add the 0 and the 1, these 2 nodes, to a queue or to a stack, right? And then we'll pop values out of the queue or out of the stack and explore them like that. So here we look at the 2 neighboring nodes, right? 0 and 1. Neither of them have been visited, so we can visit them. Start with the 0, visit the 0, and we notice that it's a 0, so we don't do anything, right? And maybe I should mention here that so far the length of our current river is 1, or the size of our current river is 1 from the root node here. Now we go to the second neighboring node, which is this 1. So we visit it, underline it in purple. We notice that it is a value 1. So we add to our size 1. So this size here becomes 2. And because we're at a 1, we continue exploring the neighboring nodes of this 1. Notice that when we were at the 0, we did not continue exploring the neighboring nodes. Here we do. So we look to the right, and we visit the right node, and it's a 0, so we stop. Then we look below it, and it's another 0. Whoops, it's another 0, so we stop. We don't explore further. And of course, to the left of it, there's nothing. And above it, right, above this 1, we do have a neighboring node, right? We are here. Above it, we have a neighboring node. But notice that it's underlined. It's already visited. So we skip it. And of course, in our algorithm, we're not going to be underlining values in purple. What we'll be doing is we'll be storing, probably in some kind of auxiliary matrix, we'll be storing a Boolean value, like a true or false value, telling us whether or not a node at a specific column and row has been visited. And we could, of course, perhaps use a hash table, though here, having an identical sized matrix of Booleans probably makes the most sense. And again, we will really dive deep into this in the code walkthrough. But so now we've finished exploring our river. We've encountered only 0s as the last sort of neighboring nodes. So we can grab our current size of length 2 and add it to some kind of final array of solutions. So now we continue iterating through our matrix. Go to the second value, which is a 0, right? Because we started here in the first row, first column. Now we go to the second value, first row, second column. We visited this value already, so skip it. Don't even think about its value, just skip it. Then we go to this one here, the 0. So we visit it. And we see that this 0 is, or this value is a 0. So we skip it, right? There's nothing to explore. We sort of apply our breadth first search and depth first search algorithm here, but because this value is a 0 and not a 1, we skip it. We don't further explore its neighboring nodes. Then we get to the next one, which is a 1. We visit it. Because it's a 1, we mark the size here. And then we explore all of its neighboring nodes. The left neighboring node is already visited, so we skip it. The right neighboring node is not, so we visit it, and we notice that it's a 0, so we don't do anything, and we just skip at this point. And then the bottom neighboring node is also a 0. It's unvisited, so we visit it, but then we notice that it's a 0, so we stop there, we don't do anything else. Now we can grab our 1 here and move it to our final solutions array. We've got a 1 and a 2, a river of size 1 and a river of size 2. So now we move to the last value in the top row, which is a 0. This 0 we can just skip because it's already been visited. Then we go to the second row. We visited this value, so we skip it. Visited this value, so we skip it. And now we go to this value. We haven't visited it, so we start exploring it. We underline it to mark that we visited it. In the code, we would, flip a Boolean in the auxiliary matrix. And because this value is a 1, we're going to mark our current size as 1. And then we're going to start exploring all of its neighboring nodes. The one above it, we visited. The one to the left of it, we visited. The one to the right of it, we visited. So we skip all 3 of those. We don't even look at their values. And then immediately below it, we have not visited. So we underline this 1. And because it's a 1, we can update our size to be 2. And we can start further exploring this one's neighboring nodes. So we look at this left node, visit it, but it's a 0, so we skip it. The right node, visit it, but it's a 0, so skip it. And then the node above it has already been visited, so we skip it. And the node below it has not been visited, so we start exploring it, underline it, right? It's a 1, so we can update our size to be 3. Then we can do the same thing. Above it, we've already explored. We can visit the left and the right, but they're both 0s. We visit the bottom, it's a 1, so we can update this 3 to suddenly be 4. And then because it's a 1, we're going to explore again. Above it, we've already visited. To the left, we visit, but it's a 0. Below it, there's nothing. To the right, there's a 1. So now we can erase this 4 and update it to 5. And then finally here, we will finally end our sort of river traversal because we visited the value to the left, we visited the value to the top, and to the right, we've got a 0, which we, of course, want to visit, but which we can skip because it's a 0. And now we can grab this 5 and move it in our final array. So we had started this entire river of length 5 up here at this 1. So now we're going to further iterate through our matrix. We'll go to this. This 0 is already visited, so we skip. This 0 we can visit, but it's a 0, so we skip it. And then here, visited, 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 visited. So we skip all of those. Then we get to here, to this 1. And here the same thing will happen, right? I'm going to skip through some of the steps here, but we're going to visit this 1, then visit this 1, and then we'll be done. And we'll have a river of size 2. So we'll add the 2 here. And then we will go down here to this 1. We'll see that it's unvisited. So we'll visit it, and we'll get a river of size 2. Again, I'm skipping some of the steps because they're really redundant at this point. And then we're done, right? Every other node that we will explore in the matrix will have been visited. And so at this point, we're done. We've finished. And we found, right, our array of solutions. So that's how the algorithm works. Now, in terms of space and time complexity, the time complexity is going to be O of, and here it's important that we be careful with our variables. It's going to be O of W times H, where W is the width of the matrix, so the length of a row, and H is the height of the matrix, so the length of a column. The time could also be expressed as, O of n, where n is the total number of elements in the matrix. Because at the end of the day, what are we doing in this algorithm, right? We're visiting every single node, and that's it. Because whenever we visit a node, we mark it as visited, right? So we'll never visit it again. Or if we do visit it again, we'll just skip it immediately. So it'll be like a constant time operation. And for nodes that we haven't visited, right, and that we are actually like exploring, when we look at all of its neighboring nodes, all we're doing is our constant time operations, right? We're getting up to 4 neighboring nodes. And when we get these 4 neighboring nodes, we end up either skipping them because we've already visited them, or we end up just visiting them for real, which means that later on in the algorithm, when we get back to them, we'll skip them because we've already visited them, right? So in total, all we're doing is visiting every node about once, and maybe, peeking at it when we're exploring neighboring nodes, but skipping it because we've already visited it. And because every node has at most 4 neighboring nodes, that's a constant time operation to look at 4 neighboring nodes that have potentially already been visited. So that doesn't really add to our time complexity, if that makes sense. It's not as if every node has, a variable amount of neighboring nodes. No, every node has only up to 4 neighboring nodes. So the time complexity is going to be O of n, or where n is the total number of elements in the matrix, or O of WH, where W is the width, the length of the row, and H is the height, the length of the columns. And the space complexity is going to be the exact same, O of W times H, because we're going to be building this auxiliary data structure, which is just going to be a matrix of the exact same size. And in the matrix, we're going to hold Booleans, false or true, basically, determining whether or not a specific node is visited. So as you can imagine, it's just going to be O of WH space. And of course, the solution array here is never going to have take up more space than this auxiliary matrix, because it's only going to be a one-dimensional array of rivers, or of river sizes. So that's it for the algorithm. That is how the algorithm works. Once again, this is one of my favorite ones because I just find it really beautiful how you can mark these nodes as visited and end up traversing this entire graph in a kind of complex way, right? In a way, keeping track of all of these sizes and keeping track of all of this state in the graph without having to visit it or to do an obscene amount of computations, purely because of this visited matrix that you're keeping track of. And so now let's dive into the code walkthrough so that I can really show you how sort of elegant this solution is. All right, so we've got our river sizes function defined. It takes in a matrix containing only zeros and ones. And the first thing we're going to want to do is to initialize our sizes array. This array is going to be the array that we return at the end of the function, and it's going to contain all of the river sizes. The second thing we're going to want to do is to initialize our auxiliary matrix, right? And this matrix is going to be exactly of the same size as our input matrix, but every value in it is going to be a Boolean that determines if the node at that sort of row and column in the input matrix has already been visited. So for that reason, we're going to call it visited. And depending on your language, all you're going to do is copy the matrix and replace every value in it with false, because at the beginning, we haven't visited any node in the matrix or in the graph. So is every node visited? No, false. So in Python, we'll say false for value in a row, for row in matrix. And now we've initialized our visited matrix. And then we can start iterating through the input matrix, row by row, entry by entry, visiting every single node, right? So this is just going to be done in a couple of for loops. For I in range len of matrix, for j in range len of matrix at index I, because remember, the matrix doesn't necessarily have the same width and height. So here it's important that, in the second for loop, which is the sort of columns in the for loop, that we iterate through the length of the specific row that we're at. Or, we could replace this I with 0 if we wanted to, because we know that every row is going to have the same length. But so inside this for loop, at every node that we're at, we check if it's visited, right? If visited at index I and index j, then we just continue, right? Otherwise, we can call probably a helper function that we're going to call traverse node at index I, j, passing in the matrix that we are, handling, passing in our visited matrix, and passing in our sizes array. And that's it for our main function. At the end of these two for loops, we can just return the sizes array. So before we start writing this traverse node function, I really want to emphasize the beauty of this main function here, where, all we're doing is iterating through the entire matrix, right? Iterating through every element. If it's visited, if it's marked as visited in our visited matrix, so if this is equal to true, right? Then we can just continue and skip it. Otherwise, we're dealing with an unvisited node, so we should traverse it. Okay, and that's when we call this traverse node method. So now let's define traverse node. Traverse node, we said that it would take in two indices, I and j. It would take in the matrix, it would take in the visited matrix, as well as the sizes array. So, what do we do here? Well, remember, when we call the traverse node method, we're essentially potentially dealing with a brand new river. So immediately we want to initialize our current river size to be equal to 0, right? Because this is potentially a new river. We're not sure yet, because we could be dealing with with a node of value 0, which would be land. But even if it is land, then the current river size is 0, right? And if it is a river, if it is a 1, then we're going to update this current river size. And then we're going to apply depth first search. Here you could apply breadth first search if you wanted to. But so the way depth first search is going to work, and we'll do it iteratively so as to not use recursion. If you are a fan of recursion, you could, of course, write this algorithm recursively, and it probably wouldn't affect the space complexity just because we've got this visited matrix, which already kind of inflates the space complexity of the algorithm. So the recursive calls wouldn't really affect the space complexity. But either way, we're going to do this iteratively. So we'll declare an array of nodes that we have to explore. So nodes to explore is going to be an array, and each array, or it's going to be an array, right? And each value in this array is going to be a node that we have to explore. Okay? So the first node right now that we have to explore is the node located at indices I and j. So I'm adding a little array here. And so this nodes to explore array is going to have a bunch of arrays in the form of, x, y, where x and y are the row and column indices of the particular node. Right now, since we call traverse node only on this one node, we only have one node to explore. Okay? And so then we can say while the length of nodes to explore is truthy, in other words, while the length of nodes to explore is not 0, while we still have nodes to explore, the current node, the node that we're really exploring right now, is going to be nodes to explore dot pop, right? So we pop out the final value in this array. And so in this way, we're essentially treating this as a stack, right? Our nodes to explore array is a stack that we're going to be pushing values to, all of the neighboring nodes that have value 1, right? Or all the neighboring nodes, period. We're going to be pushing them to the stack, and then we're going to be popping them one by one. So that's essentially depth first search. And of course, again, we could do this recursively. And if we were to apply breadth first search, we would use a queue instead of a stack. But so once we've popped the value, right, we can say that our current I index is going to be, of the current node, is going to be current node at index 0. J is going to be current node at index 1. And then, this is the critical part here, we have to check if it's visited. If our node is visited, so if visited of I of j is truthy, then continue. We don't want to do anything else at this point, right? So here, you can think back to the conceptual overview. When we were looking at neighboring nodes, which we added to nodes to explore, you'll see how that works in a second, and we're starting to explore them, if they're visited here, we just continue, we skip them, okay? If they're not visited, if we get to line 20, then we set them as visited. Visited of I of j is going to be equal to true, right? This is exactly what we were doing when we were underlining the values in the conceptual overview. And then we have to do another critical check, which is if matrix I of j is equal to 0, then continue again. In other words, if we're dealing with a piece of land now that we hadn't visited, but that we just marked as visited, if it's a piece of land, skip it, because there's nothing to do after that. We don't want to visit the neighboring nodes of a piece of land, because if we get to a piece of land, then any one that might be neighboring that piece of land is not part of our current river, right? And so then, once we are on line 23, we know that we are dealing with a node that we had not previously visited. We know that we are dealing with a node that is a river, because it has a value 1. And so we can update current river size by 1. And again, if the first call of traverse node here on line 8, when we get here and we set current river size to 0, we set nodes to explore to be the node that we called traverse node with. And so we update current river size to 1. Plus equal 1, which is going to be 0 plus 1, so it's going to be 1. All right, so we're almost done now. Once we've done that, because we're dealing with a previously unvisited 1, we want to start exploring its neighboring nodes. So we're going to say unvisited neighbors, I can spell neighbors correctly, unvisited neighbors is going to be equal to get unvisited neighbors, passing in ij matrix and visited. And so this is going to be another helper function, get unvisited neighbors, that's going to do exactly what it says. It's going to get all of the unvisited neighbors of our current node, and it's going to add them to our nodes to explore array. Or rather, it's not going to add them. It's just going to give us an array of these unvisited neighbors, and then we'll say, for neighbor in unvisited neighbors, nodes to explore dot append neighbor, right? So we append every neighbor in the unvisited neighbors to our nodes to explore. And here it's important to mention that these unvisited neighbors don't really affect the space complexity, because at most there are 4 unvisited neighbors, and then we just append them to our nodes to explore, and we kind of forget about this variable. And our nodes to explore is also never going to affect the space complexity, because even if we were to explore every single node in one call of traverse node somehow, we would realistically never have more nodes in this array than the total number of nodes in the matrix. And we would never even have that number, right? So the space complexity is never going to be affected by this nodes to explore array. But okay, so we've gotten the unvisited neighbors, we've appended them to our thing, and now we're done, right? Like, we keep iterating through this while loop, because now that we've appended a bunch of neighbors, unvisited neighbors, to our nodes to explore, this while loop is going to get hit again, right? And the length of nodes to explore is no longer going to be 0. And so we're going to go through all this logic over and over again, updating current river size by 1 if we're dealing with other nodes of value 1. And that's it. And so when we finally get out of the while loop, then we can say if current river size is greater than 0, then sizes.append current river size, right? So if we have an actual river, then add it to our sizes array, which we had passed here. And that's it. And now the last thing that we do is we write our get unvisited neighbors function, which takes in an I, a j, a matrix, and visited. And so this is an important function to get right, because this is where we can get a bunch of sort of like off by 1 errors. Remember, we have up to 4 unvisited neighbors. So we'll first declare a variable called unvisited neighbors, right? And it's going to be just an empty array. And then we're gonna check that the 4 neighbors are actually potentially valid neighbors. Because remember, if we're in the top row, then there's no neighbor above us. If we're in the leftmost column, then there's no neighbor to the left of us, right? So we have to do a bunch of if conditions or if statements. If I is greater than 0, and so if I is greater than 0, that means that we're going to look at the neighbor above us, the neighbor at index I minus 1. Because if I is equal to 0, then there's no neighbor above us. So if I is greater than 0 and not visited of I minus 1 j, the neighbor above us, and if we have not visited the neighbor above us, then unvisited neighbors dot append I minus 1 j, right? So we append, like the neighbors are this format, an array of 2 indices. So we append the indices of the neighbor above us, I minus 1 and j. If we are not in the topmost row and we have not visited the neighbor above us, then we append it. Similarly, if I is lesser than len of matrix minus 1, so if we are not in the bottom row, and if we have not visited I plus 1 j, right, the neighbor below us, then unvisited neighbors dot append I plus 1 j. Okay? And then similarly, we're going to do the same thing with the left neighbor and the right neighbor. So this is kind of like grunt work, right? But it's necessary. We have no way to avoid it. If j is greater than 0 and not visited I j minus 1, so if we're not in the leftmost column and we haven't visited the left neighbor, then unvisited neighbors dot append I j minus 1. And then finally, if j is smaller than len of matrix 0, right? Because we have to make sure that we're now dealing with a row. If it's because j is like the column index. If j is smaller than the length of the row minus 1, and we haven't visited it, so and not visited I j plus 1, the neighbor to the right, then we can append unvisited neighbors dot append I j plus 1. And finally, we can return unvisited neighbors. Now, one thing that's important to note, okay? One thing that's important to note is that in this get unvisited neighbors function, we can agree that we make sure not to add neighbors that we have visited, right? We only add neighbors that are not visited, right? In each of these if statements, we check that a neighbor is not visited. So then you might be thinking, okay, we only have neighbors that are not visited. Then we add all of these unvisited neighbors. That's why we called them unvisited neighbors. We add them into nodes to explore right here. So why do we need to check here on lines 18 and 19? Why do we need to check if a current node has been visited? We could remove that because we know that all the neighbors that we've added to nodes to explore are unvisited. That is incorrect. Reason being, you can imagine if you're dealing with a very big matrix, you might add a specific node that is unvisited at one point. You might add it to your nodes to explore, but you might not get to it for a while. You might visit a bunch of other nodes first. And these other nodes might kind of twist in the graph and eventually lead once again to the node that you had unvisited and that you had added in this nodes to explore thing. Then you might visit that node. And so at that point, the one that you had in this nodes to explore array might be visited. In other words, like you could have at one point something like this, 1, 1. You've got the unvisited node 1, 1. Then you've got a bunch of other nodes. And then you've kind of looped in the graph to get to a point where you again add 1, 1 here. And so then you pop this 1, 1 off of the stack. You visit it. And by the time that you get all the way back here, this one has been visited. And so it's important to make this check here. Otherwise, you will get an erroneous answer, a wrong answer. And that's that. That's how this algorithm works. So let's do a quick recap, right? We have our visited matrix, which we initialize to have false everywhere. We iterate through every element in the matrix. If at any point it's visited, we continue. Otherwise, we traverse it. Traversing consists of setting a current river size to 0 and setting a nodes to explore stack, because we're doing depth first search iteratively, with our current node. And then we kind of do this while loop where we continuously explore all the nodes that we add here. If they're visited, we skip them. Otherwise, we mark them as visited. Then, if they're equal to 0, we skip them because they're land, meaning that they mark the end of a river in that side. Otherwise, if they're not land, we update the river size. Then we get all the unvisited neighbors. Note that getting all the unvisited neighbors is just an O of 1 operation, because all we're doing is doing, O of 1 checks, checking if an index is greater than 0 or smaller than a length, checking if a Boolean in a matrix or at specific indices in a matrix is true or false, and then appending a value to an array. So this is just O of 1 time. Same for this. Adding up to 4 neighbors to nodes to explore array is only an O of 1 operation. And finally, once we run out of nodes to explore, we check if the current river size is greater than 0. And if it is, we append it to our sizes array, which we finally return up here. And that's it. That is it for this algorithm. As we said in the conceptual overview, this is going to run in O of WH time, and it's going to run in O of WH space, where W is the width of the input matrix and H is the height of the input matrix. You could also say O of N, where N is the total number of elements in the matrix. And that's it. It's a beautiful algorithm, in my opinion. I hope you really enjoyed it. I hope this video was helpful, and I'll see you in the next one.